and welcome back to Diksha Karnataka YouTube channel, and today in the Sankalp KCET 2026 series I am going to discuss the third part of the chapter electric charges and field, that is Gauss law. We have already discussed the chapter in previous two parts. Today is the last final part of the theory section. After this we will also cover the PYQs of KCET and PYQs of JEE as well. Yes, we are going to cover JEE PYQs as well as KCET PYQs from this chapter. All the chapters, basically all the chapters from your first PU, second PU. We have started with second PU chapters because that is the chapters that you are currently studying in your college. So you have some fresh memories of it, and many cases you don't understand everything that is being taught in your college. There are some knowledge gaps. So for that we are bringing you Sankalp series, right? And if you wonder that why should I watch from YouTube, then here is our result from last year. Those students, they have studied from our KCET 2026 batch, and you can see them. So Prajwal was our highest rank holder, he got 171, and all of them have studied from our YouTube series alone. They are not our Diksha students, they are our YouTube students, right? So next year this can be you can your photo, your picture can be over here, your name, your rank, and you can come and meet us like most of them have come to our office and meet us, right? So if you still in doubt that whether I should study from YouTube, these should be your inspiration, and you should definitely watch all of our series. We are not only doing it for physics, we are doing it for chemistry, we are doing it for mathematics, also biology for KCET as well, right? Now let's continue with the chapter summary that we have already discussed in our previous two parts. So if you have forgotten that, in the first part we have discussed electric charge, Coulomb's law, electric field lines, as well as conductors and insulators, basic properties of charges. In the second part we have discussed mostly electric dipole moment, electric field due to dipole for two different positions, dipole in an external field, the torque acting on a dipole, basically. These all, everything we have discussed in our second part. Today in the Gauss law part we are going to discuss electric flask, then we have charge distribution, Gauss law, and application of Gauss law. Okay, now some students call it Gauss law, some students call it Gauss's law. Both are correct, so don't worry about it if you are wondering about it. Now let's start with the very basic concept, which is electric flask. Electric flask, what is electric flask? A liquid flowing with velocity v through a small flat surface ds. Suppose you have to imagine that a liquid, for example, a liquid is flowing through a pipe. Okay, now in physics the liquid flowing through a pipe is not sufficient, so you have to define it properly. So a liquid is flowing with the velocity v. The velocity of the liquid is also known, it is constant, okay, with the velocity v through a small flat surface ds. Okay, the surface area is ds in a direction normal to the surface. Normal to the surface means, we will see that, just wait for a second. In a direction normal to the surface, the rate of flow of the liquid is given by the volume. So when you are talking about liquid, then you have to talk about volume. How much liquid is flowing through the pipe? How do we know that? For that you have to understand or estimate how much volume of liquids. For example, water. You are watering your garden or you are watering some place. So how much water is actually going there? For that you have to determine or measure the volume of liquid that is coming out of the pipe. Okay. So the volume crossing the area per unit time, okay, that is given by V into ds. This is the measurement of the volume that is going out through this. So this VDS is actually the volume of liquid that coming out of the pipe and represents the flask of liquid flowing across the plane. So this is how we determine flask. Now flask is basically for liquids. Now same thing we will also apply for electric field as well. Now let's see. So here we have a pipe through which the liquid is flowing through it, and this is the surface area, and velocity and surface area basically normal to each other, right? So here you can see that the volume, this is the surface area, so they are normal. Normal means basically the perpendicular direction. This angle is 90 degrees. That is the meaning of normal, if you forgot about it, right? So here you can see that the ds and v are normal to each other. Now, so this is the normal. Now what will happen if the area is not normal? For example, here the flux is given by v into ds or v into delta s. Now what will happen if the area is not normal? What is the meaning of that? So you have purposely pinched the opening of the pipe so that the liquid is not normal to the opening. So here you have crossed, or you have cut it such a way that the liquid is not normal. So what will happen? The fluid is still coming out in this direction, but the surface area is pointing in this direction. So there is an angle between them. So if you trace them back, you will find some angle, say theta. So in this case it is no longer normal. So in that case, what will be the flask? In this case, flask will be given by vds cos theta or v delta s cos theta. Okay, now let's move on. For the case of electric field, we define an analogous quantity. Analogous quantity means, which is almost similar to that, but obviously electric field is not liquid, so that's why we call it an analogous quantity. Okay, so analogous means which is similar thing, and call it electric flask. So here this is called electric flux. Previously it was normal flux, now it is electric flux. We should, however, note that there is no flow of physically observable quantity, unlike the case of electric flow. So in case of electric flow, the liquid is flowing. In case of electric field, there is no such flow, but the field lines which is pointing in particular direction can be considered to be a like of flow. Okay, so let's see that. So here, as you can see, the flow is given. So electric field can be treated as the velocity vector, is similar to that of the velocity vector. Just a second. So here electric field can be considered to be the velocity vector. Surface area is the same, and if they are normal, then the electric flask is given by delta phi or d phi. Sometimes we can in differential form we can write it as d phi as well, equals to E into delta S. So in terms of differential, we can write d phi equals to E ds. Both notations are fine, right? Now let's move on to the next. Here we have the angle. As usual, in the second case we see that the angle was not normal, right? In that case you can see that surface area is not normal but pointing towards some other direction, and the angle is given by theta. So what will be the flask? Electric flask will be given by E delta S cos theta or E dot delta S. E dot delta S in terms of vector, or you can say E dot ds. Now area and electric field both are vectors. Okay, so you have to but flask is a scalar quantity. Flask is a scalar quantity, so it should be a dot product. It should be a dot product, right? Now let's see one simple question. Okay, a charge particle Q is placed at the center of a cube of length L, A, B, C, D, E, F, G, H. Another same charge Q is placed at a distance L from O along the line parallel to AB. So you can see that here we have a charge placed inside a box, and another similar charge is placed, but it is outside the box. This charge is kept inside the box. Okay. Then the electric flask through the face BCGF. So what is the electric flask through BCGF? Now you might think that those who have studied Gauss law, this question is based on Gauss law. Actually it is not. This question is simply based on the concept of flask. Okay, it is not based on Gauss law, even though there is a cube, there is a charge. Okay, this is simple concept of electric flask, not based on any Gauss law. So they only asked you what is the net electric flux through this surface. Okay, now what is the flux due to this charge Q? So the flux means if there is a charge over here, then there will be electric field. Okay, this is a positive charge, so all the electric field will be outward direction, right? And because of this Q also there will be electric flux, but it will be in the, this is also outward direction. Okay, this is also outward direction, so due to one charge, due to this positive charge, it is in this direction, and due to the second charge it is in the opposite direction. Okay, now if you consider this is the surface, then on the surface the flask on the right hand side or towards the right, and flask in the left hand side or towards the left, they will cancel each other. Okay, they will cancel each other. So net flask in this case will be 0. Net flask will be 0. Sometimes I pronounce it flask, but it is flask. Okay, flux. So flux will be 0. Okay, net flux will be 0. So be careful, this is a trick question just to confuse you, but don't get confused. Just apply basic physics law. Okay, it is not based on Gauss law. It is only about single surface, not through the entire box. If it is an entire box, then you could have applied Gauss law, but here it is not required. Now there are three different types of charge distribution. Okay, there are three different types of charge distribution that you should be aware of. Okay, charge distribution means what? Charge distribution means we have seen in electric flask, we are taking a small area ds, okay, or delta s. Okay, so this is called a in case of electrostatics, it is very important to know in small areas how the charge are distributed. Now that can have three different types of charge distribution. Okay, not only surface, there are two other obviously. First is line charge distribution. Okay, this is called line charge distribution. What is line charge distribution? Line charge distribution, as the name suggests, here we have a line which is basically electrically charged. Okay, so charge is placed on this line, so it is actually charged. There are some charges placed on this line. Okay, now if it is uniformly charged, how can we find the charge distribution? Okay, if it is, even if it is non-uniform charge, you can find the charge distribution. Now charge distribution, line charge distribution is generally written by or represented by this symbol lambda. Okay, it is represented by the symbol lambda, and it is given by, if you take any small portion of the line, if you take a very small portion of the line, and if the charge in that portion, say delta Q, charge on that small portion is delta Q, and length of that portion is delta L, then this is the definition of the charge distribution. Now you can take this as limit delta L tends to 0, and you can make it as dq by dl as well. So dq by dl can also be considered as line charge distribution, line charge density. This is called line charge density. Right? So this is the measure of how much charge is there if I cut a small portion from this wire, and how much charge I will get. So this is a very unique and important way to understand how charge is distributed across the length of this wire. Okay, surface charge distribution. Okay, now surface charge distribution is almost similar to that of line charge distribution. Only thing is that here we have a surface instead of a line. Here we have a surface. So here we have a surface, and we have given some charge to this surface. Okay, now if you take a very small portion from this, say delta S, and this portion, suppose it has a small charge, say delta Q, then what is the surface charge density? Surface charge density is denoted by symbol sigma. Okay, this is called sigma. It is like a zero wearing a cap. Zero wearing a cap. Okay, and it is denoted by same thing, limit delta S tends to 0, delta S by delta Q. Now if it is a symmetrical surface, then sorry, just a small mistake, it will be delta Q by delta S, that is dq by ds. Okay, if it is a symmetrical surface, and if you know the total amount of charge, then you can, for symmetrical surface, complete surface, for example a spherical surface, if you apply say a charge Q and you know the total surface area S, then surface charge density can also be calculated by total charge divided by S. Okay, this is also a possibility. So don't always think this is about small charge, even though yes, this is small charge. Okay, and it is helpful for randomly distributed charge or unequal shapes or uneven shapes. It is very, very handy, but most cases we will be handling symmetrical surfaces. Most cases we will be handling symmetrical cases where surface charge density we will calculate using this formula Q by S. Okay, now continuous charge distribution. The third charge distribution is volume charge distribution. What is volume charge distribution? Now instead of having a surface, here we have a volume. Here we have a volume, three-dimensional. Okay, like a apple. Now if you take a small portion from that, cut out, okay, and if you take that out, then again say the volume, say delta V, and charge inside is say delta Q, then surface charge distribution rho is given by limit delta V tends to 0, delta Q by delta V, or dq by dV. Okay, those who are specifically interested in JEE, you have to remember the differential definitions as well. For KCET not required, but for JEE it is very much required. Now volume charge distribution, we have not very important application in KCET, but as I said, in JEE it has a lot of applications. Let's move on. So these are the toppers from our Diksha in-house campus. We have a lot of colleges, PU colleges across Karnataka, and lot of pre-university colleges for other states as well across South India. And these are the results from our PU colleges in Karnataka. So you can see that many students are doing well in KCET, and if you want to take admission in any of our Diksha campuses, please connect with us and call the number given in the description of the video, and our representative will contact you for any further assistance. So if you want to take a long-term course, or if you are interested joining from second PU, or if you want to refer your friends and family, those who want to study their first PU classes, please don't forget to contact the number below and join us for offline classes as well. Now let's move on to the next part, which is Gauss law. Okay, or Gauss's law. What is Gauss law is about? So let's see. So first we have to see the statement of Gauss's law. So electric flux through a closed surface S. Electric flux through a closed surface S is given by Q phi equals to Q by epsilon naught. Okay, so closed surface means it has to be some closed surface. It can be like this, it can be like this, it can be like this. As long as the surface is closed, okay, any type of surface, Gauss's law or Gauss law is valid. It does not depend on shape and size of the surface. So if you have a charge, say Q, inside the surface, what is Q here? Q is the total charge enclosed by the surface. Now this can be one single charge, this can be one single charge, this can be multiple charges. Okay, but total charge combined should be given by Q. It can be one charge, it can be multiple charges. Any charge outside the Gaussian surface we will not consider. We will not consider any charges which is outside the surface. So this electric field is on the surface of the conductor. Electric field is on the surface of the conductor. If you take a very small portion of the surface area and then you multiply E dot ds, and then if you sum all such areas across the surface, you will get this as E dot ds equals to Q by epsilon naught. Okay, so here you can see that we have some charges Q kept in a spherical surface. So delta S is the surface area, E is the electric field, and you can apply Gauss law and calculate whatever is the electric field. Okay, there are few points that you have to remember about Gauss law. Based on these points, in board exams as well as in KCET exams, you can expect some MCQ questions. Okay, we will see some questions in our previous year question paper solutions when you are doing it. Okay, so don't ignore these points. These are also very, very important. So what is Gauss law? Gauss law is true for any closed surface, no matter whatever is its shape. No matter whatever its shape, Gauss's law is valid for all closed surfaces. All closed surfaces, Gauss law is valid. Here Q means the formula. In the formula we seen Q includes the sum of all charges enclosed by the surface. Okay, it includes all charges enclosed by the surface. The charges may be located anywhere inside the surface. Okay, don't assume or don't think that charge is always located at the center of a spherical surface. Don't have that misconception. That is a very common misconception. Whenever we are talking about Gauss's law or Gauss law, students say that it's a sphere having a charge at the center. It can be any shape or any size. It does not matter. It can be a scattered charge as well, but as long as it is within the boundary of the surface, Gauss's law is valid. Okay? Electric field is due to all the charges. Electric field is due to all the charges, but Q is only for inside the surface. Let me explain. So we say, suppose we have a Gaussian surface. This is a Gaussian surface. This the surface that we use in Gauss's law is called Gaussian surface. Okay, we will have I think we have a point for that as well. So this surface is called Gaussian surface. Now inside the Gaussian surface we have Q1, we have Q2, we have Q3, and so. Okay, we have say n number of charges inside this surface, and we also have some charges capital Q1, capital Q2, capital Q3, and Qn, capital Qn outside the surface. All small q's are inside, all capital Q's are outside. It is possible, right? So when we say electric field, suppose this is the electric field at this point. Okay, electric field, What is electric field? We have studied that electric field due to a charge distribution is sum of all the electric fields due to all the charges, right? So if you try to find the electric field at this point mathematically or using the formula of electric field, you have to consider all the charges. You have to consider all the charges, not only inside but as well as the outside charges. So all the charges will have some say on the electric field at this point. Okay, all the charges inside, outside, all the charges will have some say on this electric field at this point. But the Gauss's law, where we write, as soon as we write E dot ds, okay, as soon as we write this q by epsilon naught, this q is only the sum of small q's, that is whatever charges are inside. It does not include the charges which are outside. Okay, so this is always true. This is always true, where this electric field can be due to small q as well as capital Q. This has small q as well as capital Q, but this charge is only small q. Okay, so be careful about this as well. The surface that we choose for the application of Gauss's law is called Gaussian surface. I already said this is called Gaussian surface. Gauss's law is often useful to calculate the electric field for symmetric surface. Okay, Gauss's law is handy when you are applying the Gauss law for symmetric surface. Symmetric surface means, what are the examples of symmetric surface? Spherical surface, cylindrical surface, okay, even square or cube, basically cube, they are all symmetric surfaces. But Gauss's law is valid for all surfaces, but it is useful or easy to apply for symmetric surfaces. Okay, because it is easy to complete the integration. Now let's see one question. A cubical Gaussian surface has sides of length A equals to 10 centimeter. Electric field lines are parallel to x-axis as shown in the figure. So here you can see the figure. The magnitudes of the electric fields through surfaces A, B, C, D and E, F, G, H are 6 kilonewton per coulomb and 9 kilonewton per coulomb respectively. Then the total charge enclosed by the cube is. So let us understand this question. It's a very interesting question. Here we have a cubical surface. Each has a side of 10 centimeter. So each has a side of 10 centimeter. Be careful, this is centimeter. So most cases unit conversion is very important, especially in KCET as well as in JEE. Okay, converting unit is essential to solve questions. So here we have 10 centimeter cube. Okay, each and electric field through this A, B, C, D. This is A, B, C, D. Right, ABCD is 6 kilonewton per coulomb. 6 kilonewton per coulomb. Okay, remember it's kilonewton. Kilo means 10 to the power of 3. You have to multiply. And electric field through other surface, that is EFGH. EFGH, it is 9 kilonewton per coulomb. Now, Newton per coulomb is the unit of electric field, not electric flask. So you have to convert it into electric flask, and then you have to apply the formula for Gauss's law. How to do that? First, we will calculate the net flask. Net flask. Okay. So what we know about from Gauss law? Gauss law says that net flask is basically Q enclosed by epsilon naught. Sometimes we say Q enclosed, okay, or small q, whatever you are comfortable with. Q enclosed is easy to remember. So here suppose we have some charges present inside. Okay, so that is given by Q enclosed. Now how to find this net flask? That is the challenge. So what is the formula for net flask? Flask, here this flask as you can see is coming inside the cube. Other surfaces there is no flask linked. So through this surface some flask is coming in, and through this surface some flask is going out. So what is the incoming flask? Incoming flask is given by the electric field times the area. Electric field which is incoming, times the area of this ABCD. Okay. So what is the electric field incoming? It is 6 kilonewton. 6 kilonewton means 6 into 10 to the power of 3. Okay. Times area. What is the area? Area side is 10 centimeter, right? It is given 10 centimeter. So 10 centimeter means you have to understand 10 centimeter means 10 into 10 to the power of minus 2. So whenever you are converting centimeter to meter, always multiply 10 to the power of minus 2. It is easier this way to handle this kind of questions, always. Okay, once you develop the skills of converting centimeter to meter, meter to centimeter, like this way, you will never make a mistake like other students do in the exams. They make small silly mistakes. Also, you have to understand that in KCET exam or in JEE Mains exam, you are not allowed to use any calculators. So you have to prepare, you have to train your mind of without using calculator how to solve questions. So first I suggested it last year as well. Some students followed, they scored well, some students didn't, and they lagged behind. Many students struggled with the time, keeping up with time, because they are used to solve questions using calculators, right? So calculators, you have to stop using calculators right now. Do not use calculators. Okay, that is a very, very bad habit. Now area is length into breadth. Now in this case length and breadth both are equal, so in this case it will be area is basically length square for a square. That is the formula. Now you can cancel it. You can say, okay, I can reduce this to 10 centimeter is equals to 10 to the power of minus 1, because we have converted it into meters, right? We have converted it into meters. Now what is the value? 6 into 10 to the power of 3 into 10 to the power of minus 2. Minus 1 into 2 minus 2, so it will be 6 into 10 to the power of 1, that is 60. So this is the electric flask that is going in. Okay, and this is Newton meter square per coulomb. Okay. So what is the electric flask which is going out? Now outgoing flask should be easy to calculate. So outgoing flask is given by same formula, electric field whichever is going out, times the area. Okay, so what is the electric field going out? 9 into 10 to the power of 3, and area we have already calculated, it is 10 to the power of minus 2. So it will be 90 Newton meter square per coulomb. Now unit is not necessary if you are solving it for competitive exams, but you should be aware of the units as well. Now what is the net flask? Net flask is always phi in minus phi out, always. It is not larger minus smaller, it is always in minus out. Okay, so what is in was 60, what is out was 90, so it is minus 30. So net flask is minus 30. Yes, net flask can be negative based on the polarity of the charges. Now you have to put that value over here. So minus 30 equals to Q enclosed by epsilon naught, or Q enclosed is minus 30 into epsilon naught. Okay, now what is the value of epsilon naught? It is given in the question itself. So as I said in my previous lectures as well, if the epsilon naught value is required, they generally provide it in the question itself. So epsilon naught value is given 9 into 10 to the power of minus 12. Also you can approximate this value for your solution as well. So 30 into 9 into 10 to the power of minus 12, or it will be minus 270 into 10 to the power of minus 12. 270 into 10 to the power of minus 12, or you can say Q is enclosed is 0.27 nanocoulomb. 0.27 10 to the power of minus 9, right? 10 to the power of minus 9 means we have to add 3 decimal points, 1, 2, 3. So here will be a decimal, so 0.27 nanocoulomb, and also it is a negative sign. It is also a negative sign. The charge is negative. So Q enclosed is 0.27. I just ran out of space, so I will try to fit it over here. Q enclosed is minus 0.27 nanocoulomb. Okay, so from the answers you can see this is the correct answer. Okay, let's move on. And if you want to get the PDF for this lecture, then definitely you have to join our WhatsApp channel. The link of the WhatsApp channel given in the description of this video. So don't forget to join our WhatsApp channel if you have not yet joined. Okay, all the PDFs, all the lecture updates, whenever we are posting some important updates for you, or whenever we are coming live to discuss questions with you, you have to be present in our WhatsApp channel so that you get the update. Now, field due to an infinitely long straight uniform charged wire. So this is the formula. We will come to see how we can do that in a while. So here we have a line charge, infinitely long line charge. Let us understand the meaning of that. Okay, so here we have a rod, very thin rod, okay, having charge distributed along its length uniformly. What is the meaning of uniformly? So if you take any portion from it, say suppose you take a small portion, say dx from here, and you take a same portion dx from here. Suppose the charge on this, say dq, then charge on this portion will also be dq. Okay, no matter from where you take this small portion out, the charge on each of such portions will be same. Okay, this is called uniformly charged long, very long. That means its starting point and ending point we do not know. It goes up, it goes down. Okay, very long, infinitely long charged wire. Now if you want to find electric field at a distance r from the axis of this, if you want to find electric field at a distance r from the axis of this wire, okay, so how to do that? Suppose this is the point P where we want to find the electric field. Now what we have to do? We have to construct, whenever such cases comes, we have to construct a Gaussian surface. To find the Gaussian surface, we have to find a symmetrical Gaussian surface. Suppose it's a point charge. If the charge is point, the most common symmetric object is a sphere. Okay, this is the most symmetric. Okay, we know that a sphere has infinite symmetry, right? So it is a symmetric sphere. In case of a line, okay, the most symmetric object is a cylinder. Okay, it's a cylinder. If you consider this, it will be across the surface of the cylinder, the wire is symmetric. May not be on the top and bottom portion, but along the curved surface the wire is symmetric. Why? What is the meaning of symmetric? Symmetric means even if you rotate, it should look same every direction. Okay, suppose you are standing inside a sphere at the center, even if you rotate yourself, all the points will appear same to you. Even if they rotated you, after opening your eyes, you will see that, okay, I am standing wherever I was standing. But it actually, your orientation may have changed, but still you will not feel that. Okay, that is called symmetry. Okay, this is a mathematical term. You may have studied it in your mathematics. If you have not, then go and do some googling about it and learn little bit more about symmetry. It's very interesting concept, right? Also symmetry, another example people give, it's like a mirror. If you fold it, it appears same. If they mix, then it is called symmetry. If you mix it along some direction, and if they give you same mirror images, then it called having that line is called symmetric line, right? For a sphere, it has infinite symmetry, because any direction if you fold it, it will always get similar to that of circle as well. You will get always the same infinite number of possible lines are there. Now in case of cylinder, this axis is called symmetric axis, right? So if this is the axis, then all the direction, along all direction, the electric field will be symmetric. So if you are looking here, 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 does not matter, right? That is why we choose this cylindrical surface. Now here this is the curved surface, okay, and we have chosen a specific length of length L. Okay, we have chosen a specific length of cylinder of length L, where this P located somewhere in between the cylinder. Does not need to be, and the point is obviously on the surface, but it does not need to be at the center of the cylinder, does not. Okay, because of good looks they have drawn it, the point P can be here as well, no problem with that, but it has to be on the surface. So the radius of the cylinder is R. The radius of the cylinder is R. Okay, now we are considering a length L. If the length of the cylinder is L, then what is the charge enclosed by the cylinder? What is the charge enclosed by the cylinder? The charge enclosed by the cylinder is given by charge density. Charge density means for unit length whatever is the charge, right? That is the charge density. Charge density I already defined. For unit length whatever is the charge, this is how we defined charge density. So if you take unit length, that is dx equals to 1, then whatever charge is there, that charge is lambda. For one length, that for example unitary method, for length 1 the charge is lambda. For length L the charge should be L into lambda. So charge enclosed by this cylinder will be L into lambda. I am trying to explain, so those who already understood it, they can skip this portion, but otherwise most students who don't understand in their regular classes, because the teacher thought you are very smart, they skipped similar portions, some questions, some answers, and I have seen students, they struggle it because they don't understand how this Q enclosed equals to L lambda is arrived, right? So Q enclosed is basically the total charge inside this cylinder. Okay, now we apply Gauss law, which is very, very simple. E dot ds, that is phi, equals to E dot ds equals to Q enclosed by epsilon naught. Okay, now here as I said, why we choose symmetric surfaces for Gauss law? What is the importance of it? The importance of it is that if you go to any direction, all the points are equally distant, right? R here, R here, R here, R here. So the electric field, because of symmetry, electric field is very simple thing. If this is symmetric, then electric field will be magnitude wise constant. Direction will be different. For example, if you consider a point along this direction, okay, electric field will be outward, but the magnitude on this point will be same. So electric field magnitude wise will be same, and each and every point, if you consider ds, what is the direction of ds? Here at this point, ds is in this direction. So ds and electric field, they are basically parallel. Okay, so parallel means cos theta will be theta will be 0, so E dot ds cos theta will be 1. Okay, so we can simply write this as E integration ds. Cos theta is 1, So dot product is gone. Here we have taken, if you observe carefully, this does not have any vector sign. That means this is the magnitude. Okay, so no vector sign means it is the magnitude. Now Q enclosed is given by L into lambda by epsilon naught. Now we have to find the ds. Now if you consider this section and this section, in both cases ds is in this direction and E is in this direction. So the angle between them is 90 degree. So angle between them is 90 degree means on this surface and in this surface E dot ds are 0. That means electric flux through top and bottom will be 0. So no electric flux is passing through this. So only surface area here we have to consider is the curved surface area. Only the curved surface area. Now if you have followed my bridge course class, there I have explained that integration basically represents summation. Summation, it is basically addition, right? So ds, integration ds means if you take small ds areas, small areas, and if you add all such areas, you will get integration ds. So here integration ds represents the surface area of the curved surface of the cylinder. So what is the surface area of the curved surface? Surface area of the curved surface is 2 pi r L. 2 pi r L equals to L into lambda. That this formula also we have discussed in our bridge course class. Okay, so from here you can cancel L and L. So from there you can say E equals to lambda by 2 pi epsilon naught r. Okay, now as I said, 1 by 4 pi epsilon naught is easy to remember. That's why I have converted this into this form. This is a form that you can remember, or this is also a form that whatever form you are comfortable with, you can remember any of these two forms. Okay, 1 by 4 pi epsilon naught has a fixed value 9 into 10 to the power of 9. That's why I kept it 4 pi. So basically what I have done, I have multiplied 2 in the denominator as well as in the numerator. Okay, that's why you see there is a 2 lambda over here. Okay, and just rearranged it. So 1 by 4 pi epsilon naught here and 2 lambda by r over here. This is just a style of writing. You can always use this formula as well. Now, next one, I am not going to do the derivation. Here we have a uniformly charged infinite plane conducting sheet. Okay, here we have infinitely plane charged conducting sheet. Okay, here the electric field on the surface, both of the surfaces, it is given by sigma by 2 epsilon naught. It is, as you can see, electric field near a infinite long conducting surface does not depend on the distance from the surface. So if the sheet is infinite, so previous case it was a infinitely long wire. Here we have a sheet. Sheet means like the sheet of your book. Sheet paper, the exam on which you write the exam, the sheet, right? The same thing, but it's infinite. It's very long, like a banner. You have seen the banner, sports banner that is there in your college, where all the toppers of your colleges are mentioned in a picture like a huge banner. So that you can consider to be a sheet. Okay, so sheet of paper. So if it is a conducting sheet, the electric field is given by sigma by 2 epsilon naught if it is a very long. Now generally, obviously, infinite sheet is not possible. So in case this is a finite sheet, if it is a finite sheet, then you can apply this formula if the point is very close to the surface. If the point is very close to the surface, that means the dimensions of the sheet and the distance that we are considering is smaller compared to the size of the sheet, then you can basically consider this formula. Okay, so physics basically taught you how to use approximation, how to approximate complex things into simpler values. Okay, so obviously if you consider the sheet that I was talking about, the banner that is posted in your college about all the toppers pictures are there. So if you stand very close to the sheet, and if the sheet is charged, okay, very close to the surface means say 5 centimeter, 10 centimeter or 15 centimeter, then this electric field, this formula is very much valid for that distance. Okay, maybe if you are standing 2 kilometers from there, then it is not valid. Okay, if you are standing say 100 meters from that sheet, this formula is not valid. But if you are standing say 50 centimeter or 100 centimeter, then this formula is well and within the limits. Okay, now here we have a last case is the Gaussian surface for thin spherical shell. Thin spherical shell. Here we have a very thin shell. Shell means what? First of all, let us understand shell. Shell means if you have seen eggs. Okay, eggs. You may have eaten egg. Some of you are vegetarian, do not eat eggs. Some of you, but you must have seen eggs, right? The outer side of the egg is very thick, and if you break it inside, you see the white and yellow part of the egg, right? So the outer thin wall, if you break it, you see that the inside of the egg, after you take out the yellow and white part out, it basically appears to be hollow, right? It appears to be hollow. So that crust, the thick crust, is called a shell. Okay, so that means inside this there is nothing, not even egg yolk or egg white, right? So inside of this is basically hollow. Or those boys who play cricket using tennis balls, once the tennis ball is broken, you see that inside that tennis ball is basically hollow, right? They have a thick covering and inside it's basically hollow. So it is like that tennis ball. Okay, so inside it is basically hollow and there is a thick covering outside. This is called a shell. Okay, so first we have to consider this shell is electrically charged. Okay, the surface charge density of the shell is given by sigma. Surface charge density is given by sigma, and we are trying to find the electric field outside the shell. Electric field outside the shell, not inside. Very, very important about it. So first we have to consider this entire, we have to construct a spherical surface, spherical Gaussian surface. Always try to construct a Gaussian surface. So in the previous case, if you have seen, in this case we have constructed a Gaussian surface which is basically a like a cuboid. Okay, it is not exactly cube, but it's a cuboid. Okay, so all the sides, these two sides are parallel to each other. This we have tried to keep this length equal, and surface areas were important, not the actual shape. You can consider cylindrical surface areas as well, does not matter. Okay, it is called Gaussian pillbox. This shape is called Gaussian pillbox. This is also fine, this is also fine. Okay, but in this case, because it's already a sphere, the closest, most symmetrical object will be another sphere. And in this case, the center of the sphere should be same as the original shell. Okay, so here we have constructed a Gaussian surface which is also a sphere, okay, having the center at O. Now capital R represents the radius of the shell, okay, and small r represents the distance from the center. Now capital R is greater than, here small r is greater than capital R. This is the case number 1. So what is Gauss's law? Gauss's law states that E dot ds equals to q enclosed divided by epsilon naught. Okay, now as it is again it's a symmetric surface, so electric field on each point on the surface will have the same magnitude, and E and ds again are in the same direction. So E, suppose this is the point, okay, E is in this direction and ds ds is basically this direction is called ds. So E and ds again are in the same direction. So E and ds are in the same direction, means their dot product will be simply have cos theta equals to 1. This is ds. So E ds again we will take the magnitude of electric field outside and integration of ds inside equals to q enclosed. Now in this case, first let us say that total charge in this is capital Q. We will do a little bit more calculation on that, but for now assume that the total charge is given by capital Q. So capital Q by epsilon naught. Now what is ds here? As I said, ds is the surface area. Sum of all such surface area is the integration ds, that is the total surface area of the sphere of radius small r. So what is the surface area? Surface area is 4 pi r square. Surface area of a sphere is 4 pi r square, q by epsilon naught, and after simplifying you get this as electric field is 1 by 4 pi epsilon naught q by small r square. So this is the electric field formula. Now there is another formula that might come handy, so I am doing that as well. So basically what we will do, we will find this q in terms of the surface charge density. So what is the surface charge density? Surface charge density is total charge, that is capital Q, we already assumed it, divided by the total surface area of the shell. Charge in this case is kept only on this shell, right? So charge is only on this shell. So when we are considering the surface charge density, we will only consider this shell, not the outer one, only the inner one of the radius capital R. So here we will only consider the surface area of the shell, that is capital Q divided by 4 pi capital R square. That's it. Okay, so here this is the surface charge density. Or from here you can calculate capital Q equals to 4 pi sigma capital R square. Okay, now if you put that value over here, you can calculate the electric field to be 1 by 4 pi epsilon naught into 4 pi sigma r square by small r square. 4 pi cancels and you get this as sigma r square by epsilon naught r square. This formula can be handy at times. This formula can be handy at times. Now this is about shell, not about the sphere. Now sphere, complete solid sphere is not there in the syllabus, but you should remember that this formula, at least this formula, is even true even if this sphere is solid. Okay, even if this sphere is solid, this formula will still remain true. Okay, and this formula can also be true if it's a conducting sphere. It can be conducting sphere, it can be non-conducting sphere. This formula is always true. This formula can be true for conducting sphere. For non-conducting sphere, this will not work, because in that case you have to consider the volume charge density, which we are not doing in this lecture. Now what will be the inside? What will be the electric field inside the shell? Very easy. Why easy? This is the most easy part. So E dot ds equals to q enclosed by epsilon naught, that is Gauss law. Now when you are considering a spherical shell, inside is hollow. Hollow means, now this case is where r is less than capital R. Here r is less than capital R. So in this case the charge enclosed here is 0. No charge is present inside. So no charge present means it will be 0. So electric field will be 0. So electric field inside a spherical shell will be 0. And same concept is applicable if it is a shell or even if it is a solid solid conductor as well. Why I am saying that it is valid for solid conductor? In the last case also I said, because in case of solid conductor, okay, there is no charge inside the conductor. If it is a solid conductor, okay, charges will always remain on the surface. If it is a solid conductor, charges will always remain on the surface. Okay, if it is a conductor. If it is an insulator, charges can stay inside as well. Okay, for example, if it is a rubber ball, charges can stay inside as well. But if it is a metal ball, then charges will always remain on the surface. Okay, remember that. Now, if you plot the graph electric field versus distance, okay, then the graph will be like this. Now, based on this graph, we have seen lot of questions in KCET. Not only once, more than once, this graph based question actually came. Okay, so why there is no line here? Because electric field inside the surface, inside the shell is 0. Electric field inside the shell is 0, and as I said, this graph is same for spherical shell as well as a solid conductor. Okay, same graph will be there for solid conductor as well. In KCET, they sometimes ask the same question with a solid conductor. Okay, potential graph is slightly different, so that's why they try to confuse you between potential graph and electric field graph. We will see that in our potential chapter. Anyway, as you can see, electric field is proportional to 1 by r square for any points outside the shell. Now, if you remember one more thing, what was the electric field outside? Electric field outside was given by 1 by 4 pi epsilon naught q or capital Q by capital Q by r square, right? That was the electric field outside the spherical shell. So that means, so it was the shell, okay, and electric field outside is basically same as if the entire shell, charge of entire shell is located at the center. Charge of entire shell is located at the center, as if. This assumption is only valid for points outside. This assumption is not valid for points inside, because for points inside there is no actual charge, no physical charge, so the electric field will be 0 for inside. So this portion is same as for a point charge. This portion is same for a point charge, as if this is, if you are considering a point charge, the graph would be like this. Okay, point charge actually starts from the point itself and it goes like this. But for a shell there is a discontinuity here, so electric field is 0 inside, but as soon as you go out, the electric field starts behaving as it was a point charge located at the center. So very, very important graph, you have to remember it as well. Now let's see one question. Two equal and opposite charges of masses m1 and m2 are accelerated in a uniform electric field through the same distance. What is the ratio of their accelerations a1 by a2 if the ratio of their masses is m1 by m2 equals to 0.5? Now this is based on the entire chapter summary. You can consider this to be a we have already completed lot of concepts from this chapter, so this is the last question from this chapter. There will be some homework question, then before that this is a kind of summarizing the entire chapter. So let's see. So we have two equal and opposite charges of masses m1 and m2. We have two equal and opposite charges. One is say plus q, another one is minus q. This one has a mass m1, this one has a mass m2. Now they are accelerating in uniform electric field. Suppose we have an electric field, so this will accelerate in this direction. Suppose that this is the direction of electric field. The positive charge will accelerate in the direction of electric field. The negative charge will accelerate in the opposite direction of the electric field. So this is A1, this is A2. Okay. So what will be the ratio of their acceleration if the ratio of their mass is given? Now first we have to understand that what will be the force F1. So they will not automatically accelerate. First thing they will experience is force. This one will experience force F1, this one will experience force F2. So what is F1? F1 is Q into E, right? F2 will also be Q into E, but in the opposite direction. So F1 and F2 are basically equal. Okay. Now what is force? Father equals to ma, right? Father equals to ma. So F1 and F2 are equal, right? But they are different. Masses and accelerations are different. So now what is the meaning of that? M1A1 equals to M2A2. So this is as simple as that. Question might appear a little tricky, question might appear a little difficult, but if you understand the physics, if you understand the concept, the question is actually simple. Many students struggle because of this. They don't understand the concept, they don't understand the question properly, and they start panicking. Don't panic. Questions will be easy. You need to practice, you need to understand the basics. Okay. Now M1 by M2 is given 0.5. So A2 by A1 must be also 0.5. Now what will be A1 by A2 then? So A1 by A2 will be 1 by 0.5, that is 2. So the ratio will be 2. Okay, even though this question is not based on Gauss law, actually in KCET Gauss law based questions are very easy. So I have given you a question which is also easy but not direct straightforward. Okay, so here are the homework questions. You can see that. You can pause the video if you want, and also the PDF of this lecture will be available on our WhatsApp channel. So definitely join our WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. So don't forget to join it, and obviously you have to subscribe to our channel as well. Click on the like button if you like this lecture. This is homework number 2. Both homeworks, please answer them and try to mention the answer correct option in the comment below. If you are answering the first homework question, mention 1A, 2B. So this is actually homework question number 1. Okay, this is homework question number 1. Okay, Q1. And this is homework question number 2. Question number 2. I will answer all the homework questions in the comment only after 1 week of the publication of the video. Okay, and if you are watching this video after 1 week, you can go and check the answer in the comment below. Okay, so obviously I request you to subscribe, share this video with your friends so that we reach out to more and more people. As you know, we are the #1 KCET channel in YouTube. So, and we are trying to help all of you for absolutely free of cost. Please don't forget to subscribe to our channel and like this video if you are obviously watching this video. And I'll be back with PYQs, KCET PYQs first, then JEE PYQs. Till then, bye.